Welcome everyone, I am Merel van Gorp and in this video you will learn more about my research about the hydrodynamic function of keels in boxfish. The body of boxfish is completely covered by a bony shell of fused hexagonal plates, the carapace, to which they owe their box-like appearance. As you can see, boxfish are excellent maneuverers. They can accurately control their body rotations and they can easily maneuver themselves in and out narrow spaces during foraging. This is all quite remarkable considering that because of their rigid carapace, boxfish can only rely on their 5 fins. With their inflexible body, they are similar to many rigid man-made aquatic vessels, where maneuvering, hovering, and precise landing at low speeds are strongly pursued. But even after decades of engineering research, they are easily outperformed by biological systems. Therefore, it's not unexpected that boxfish morphology has been the subject of several studies of bio-inspired design. The carapace is characterized by longitudinal ridges or keels. It was thought that these keels improve the swimming performance of boxfish in multiple ways. However, these hypotheses were never tested explicitly. In this study, we investigated which of the claims about the keels are true. 5 different boxfish species were studied, each of which had a different body shape. For each species, we compared the performance of a 3D model from a preserved specimen to a model where we digitally removed the keels. This was done by simulating the water flow around the 3D models, from which we then could calculate the performances. The first hypothesis was that the keels of boxfish would reduce the energy cost for forward swimming, as is the case in the leatherback sea turtle. This turned out not to be true for boxfish. The removal of keels had only a very small and inconsistent effect on the water resistance of the body. Furthermore, the keels were set to enable the boxfish to maintain straight swimming trajectories in turbulent water. This by passively correcting whenever the body is pushed slightly off course. This was claimed for up and down rotations and left-right rotations, similar to aerodynamic self-stabilization as seen in darts. However, recent studies found that this was definitely not the case. They measured that when thrown slightly out of balance, without active intervention of the fins, the body would keep drifting off. Considering that boxfish spend a lot of time maneuvering in their spatially complex habitat, a stable body wouldn't seem suited. Because permanent course stabilization would oppose every movement, this would make maneuvering energetically costly. From our results, we could confirm for all 5 species that the boxfish body was inherently unstable for nose up, nose down rotations and left-right rotations. No relationship could be discovered between the magnitude of the instability and the keels. These parameters were only very weakly affected by the presence of keels, and differences were inconsistent. The course of the water flow surrounding the body is very little affected by the removal of keels. The final hypothesis was that the keels of boxfish work similar to the keels in boats and ships, where they are used as a passive stability system to reduce the tendency to roll. This hypothesis, which was never tested before, was strongly supported by our results. All species showed a strong increase in roll resistance by the presence of keels. This demonstrates that the boxfish is less likely to be thrown off balance when it has keels. Now we know this, the next step is to find out how this improved roll resistance by the keels could contribute to swimming and maneuvering performance of the boxfish. This knowledge can in turn be used to enhance roll stability in engineered underwater vehicles without undermining maneuverability. Thank you for your attention.